Let's jump into a few examples related to kind of pressures, densities, and fluids. So here's the first initial one that we have. And I'm going to put everything, okay, the answers in metric standard units unless it's stated otherwise. All right, so within this for part A, so notice that the volume K is given, so they're asking us for the volume flow rate. Okay, the total time elapsed is also given, so basically the volume flow rate that we have is going to be the total volume divided by whatever time has elapsed. Now 450 liters is equivalent to 0.45 meters cubed, and you should know that 1 meter cubed is equal to 1,000 liters. All right, so that's something that you should be aware of. So if I want to have this in metric standard units, it's going to be 0.45 meters cubed divided by the total time. This is in minutes, so be careful. So we got to change this back. So it's going to be 1.2 times 60 because there's 60 seconds in 1 minute. So we're going to have 1.2, okay, so times 60, and we can find out what that volume flow rate is. All right, so 0.45 divided by, and this is now 1.2 times 60 equals 2. Okay, so it's rather small there, 625, except it's meters cubed per second. All right, now if you wanted it in liters, so it's going to be 6.25 liters per second. All right, so there you have it. Okay, so that's what you would have. It looks like there's two significant figures, so you can round that off. 0.0063, I guess, if it was 2 sig figs. All right, so for part B, so that's the second one. If a fluid flows at 3.2 meters per second, so here we are given the speed, and then we have the cylinder, okay, and it gives us a radius. All right, so in this particular case, so if we want the volume flow rate, so we can't use this directly, okay, we're going to have to use the formula, which just simply takes the surface area that it's flowing through multiplied by the actual speed. All right, so this is the speed that we have. Now speed is given, area is not, but we know that it's a cylinder. Okay, so that means the area is going to be pi r squared, which is equal to pi. Notice the radius, I'm going to change back to meters. Okay, so this is what that's going to be, and now I can substitute everything back in here. So that's my area right there. So I'm going to just write it as it is and then multiply everything at the end. So that's my area, and then my speed is 3.2. And that's going to give me everything in meters cubed. Okay, so there you have it. Okay, so pi and multiplied by 0.02 squared, and then multiplied by 3.2. And so we have this tiny amount, 0.004, 021, etc. This is meters cubed per second. All right, so again, if you want this in significant figures, so I'm going to just actually put this in 4.0 times 10 to the minus 3. So two significant figures for this one. And if you want it in liters, then it would have been, 4.0 liters, okay, that you would have per second. All right, so that is it for this first example. Okay, so check, moving on. Here's this next example. It says if the blood velocity in an aorta, diameter of 0.98 centimeters, so that's actually a small diameter, it probably would be a little bit bigger, okay, but again, it depends on the individual, is approximately 23.2 centimeters per second, then how much blood would flow through in 1 hour? All right, so provide answer in liters. Okay, so let's take a look in here. So we have, okay, so we're gonna, anytime they give us diameter, radius, you're always kind of assuming that you are referring to surface area, which is cylindrical. So pi r squared is going to be, okay, our area in here. So that's going to be pi diameter, so that means it's 0 point, I guess I have to change this back. So I have to move the decimal place. Okay, so we have to kind of be careful in here. So move it 2 decimal places. This is going to be divided by 2 because we want the radius. So that's that squared. My speed, and so this one again, so I'm going to just change it back 23.2. I'm going to change it to metric standards. Okay, then how much blood would flow through in 1 hour? Okay, well, so if you want the total volume that has flown, then this is going to be the volume flow rate multiplied by the actual time, right, that passes you by. So the volume flow rate, well, that's going to be the area times the speed, and then times whatever time, okay, we have in here. So I have to substitute all of these in. So I have to substitute the area, I have to substitute the speed, and now for my time, so here's where you're going to have to be careful because it's 1 hour. So 1 hour is equal to, okay, 3,600 seconds. So because there's 60 seconds in a minute and 60 minutes in an hour. So now, if I take all of this into consideration, okay, so let's take a look what we're going to get. So here's my pi, so my r, which is 0.0098 divided by 2. This whole thing is squared, multiplied by 0.232, that's the speed, and then multiplied by, okay, so this is in an hour. Okay, so there you have it. So that's going to be, now this is in meters cubed. So if you want it back to liters, you have to multiply it by 1,000. So this is going to be 60, I guess, how many significant figures is there? So it's 2 or 1. Okay, so I'm going to just leave it. Okay, so this is going to be 63 liters per second. All right, sorry, 63 liters in total. Okay, it's not per second because it's within an hour. All right. So two significant figures. If you want it 1, then it's just 60 liters, okay, approximately. Okay, so that is it for this example. That's all that we would do. Here we have a cylindrical pipe, has a fluid flowing at a speed of 4 meters per second. If the volume flow is 10.9 kiloliters, all right, per minute, then what is the radius of the pipe in centimeters? Okay, so this is just kind of a little bit of annoyance because of all of the different units. Okay, so let's write it down. So we have the speed, so that's 4 meters per second, so that's all metric standard. And now we have the volume flow rate, which is 10.9, now this is kiloliters per minute. All right, so in this case, if we want this in metric standards, the kilo, okay, so notice that, so recall that we have 1 meter cubed is equal to 1,000 liters, or, this is really 1 kiloliter. So actually, okay, so this is the same thing as saying 10.9 meters cubed per minute. Now we can change those minutes, okay, get rid of those, and make it per second. So we can certainly do that. So let's see what that's going to give us. So 10.9 divided by 60. Okay, so 0.181 and then a bunch of 6s. So this is meters cubed per second. Okay, so we have that. So the velocity, okay, or the speed, the volume flow rate. Now we want to know what the radius was. Okay, so within this. Okay, so we have to kind of think back. So volume flow rate is equal to the area times the speed. This is going to be pi, okay, r squared times the actual speed itself, v. Now, we have all of these, right? So we have the volume flow rate, so we've just found it over here. We have the speed, okay, so we have that. So now we can find the radius. So the radius squared is going to be volume flow rate, right? So that's this right here. And then we're going to divide both sides by, so this is going to be divided by pi and then divided by v, right? So this is what we have. Let's see what this gives us. And then we're going to have to take the square root, right? So notice that because we have this, we're going to have to take the square root. So that means r is going to be equal to the square root of the volume flow rate divided by pi, okay, divided by the speed. So if I take this, because I already have the volume flow rate, so here's my answer to that. Now I'm going to take this and divide it by, this is going to be divided by pi times the speed, which was 4 meters per second. Okay, so that gives me r squared. And now I have to take all of this and take the square root of it. All right, so if I do that, okay, so I'm going to do this, okay, as a fractional. So that would have been my radius, okay, which is 0.12. Let's see. Okay, it looks like two significant figures. Okay, so this is going to be, so I'll just leave it as this. This would have been meters or just 12 centimeters. All right, so that would have been the radius that I would have over here. All right, and I mean, as you can see there, you know, there's it's quite a lot of fluid which is flowing. I mean, 10.9 kiloliters, okay, per minute, or 0.18, okay, 16 meters cubed per second. So that's quite a lot, right, that we would have in here. Okay, so there you have it. So that would have been the radius for this example. A horizontal pipe with a radius of 1.5 centimeters has a fluid moving at 3 meters per second. The pipe eventually narrows to a radius of 0.48 centimeters. Will the fluid speed up or slow down? What is the speed of the fluid where the radius has narrowed? Okay, so what has happened is kind of like this. So I guess we have some pipe, okay, and then it narrows down. So maybe something like this, and it continues on, okay, so as it flows through. So you have, so this fluid which is passing through, okay, and then it continues on in the narrowed path. So what they tell us is the following, so that we have the radius for the first one, okay, which is 1.5 centimeters, okay, so or 0.015 meters. And this one is moving at a speed, okay, so this, I'm going to call this initial, all right, or 1. So this is going to be at 3 meters per second. The pipe on the other side, so the radius, so this is the radius, okay, this is the narrowed path, okay, maybe call this 2, should have called the other one 1. It doesn't matter, so we have 0. Okay, here 0.0048 meters. And then the actual speed, okay, over here we don't know. We want to be able to find what this is, right? So we want to be able to see what this speed is. Now, first, will the fluid speed up or will the fluid slow down? All right. So if the assumption is that you have your volume flow rate, so let's let's call this that initial. If your volume flow rate doesn't change, right? So if it means the same amount of volume is flowing initially as it is in the second component, so the same amount, it doesn't change, then because it's narrow, that means it has to go faster, right? So this is going to speed up, okay, in order to meet the same criteria in terms of the volume flow rate. So that answers that. It has to speed up because it's narrowed, so more fluid has to go through it, not more. The same amount goes through, but the only way that it's going to go through the same amount is if it goes faster, because that cylindrical pipe there has narrowed down. Now, in order to answer, what the speed is, well, we can use this equation. So we're going to have our initial area times the initial speed is equal to the second area times whatever speed we have there. And this is what we're trying to find. So this isn't actually very difficult. This is going to be pi r squared times v, okay, the initial one. And then again, so pi, this is going to be the r, okay, second times v2. And we're looking for that v2. The pi cancels because you have pi on both sides. So that means that v2, so this right here, if you're solving and isolating for it, is going to be equal to the radius, okay, initially, times the speed that it's moving at divided by, okay, the radius, okay, of it is on the other side. So now we have all of this information, so I can plug it in and solve it. So the initial radius, which is going to be 0.015 squared, is going to be multiplied by that speed, which is 3 meters per second, and then it's going to get divided by that second radius, which is 0.0048 squared, okay, equals. So this actually moves pretty quick. So V2, notice it's sped up a lot. So 29.29, etc. meters per second. And if we want to round, I guess we had what, 2 significant figures was the lowest, so it's about 29 meters per second. So that's pretty quick. So notice it went from 3 to almost 10 times as fast. And that's because of the narrowing, and that indeed will happen when you are narrowing down and you still want to maintain the same amount of volume flow rate. So that's this example. This next example actually ties in to the previous one, all right? So this kind of goes hand in hand over here. It says that in the above example, would the pressure in the 1.5 centimeter radius portion be bigger or smaller than the pressure in the 0.48 centimeters portion? Okay, so explain. Now, so this is very interesting, and it says, hint Bernoulli's principle, and indeed that's going to guide us. We're assuming it's on the same horizontal, and that's why we're going to be using Bernoulli's principle and not Bernoulli's equation, where the height would also matter. So here they're at the same height, all right, in terms of the fluid flowing horizontally. So if you look at this, there's really 2 terms. Now, this comes from the fact that kind of these 2 components remain the same, where you have the pressure. Okay, so let's assume that initial one, this is the pressure in that first, okay, pipe right here. So that's the pressure in this one. And then P2 is going to be the pressure over here. All right, so that's what we're going to have between the 2. So with those 2 components, okay, so these are the 2 pressures. What you notice is the following. No matter what the actual fluid is, okay, so notice the density won't change, right? So this density will not change. So this is not going to have any impact. It looks like there's a half in front of that density, so that is constant. So really the only thing that's changing, okay, is the speed. So what we notice is that this speed was approximately 3 meters per second. And then V2 had a speed of, 29 meters per second. Okay, you see that up above there, right? So it's 10 times more. So this entire term that you would have, so this term over here that you have, right? If you take the 3, okay, and square it with the same density, in comparison to this, right? So that term skyrockets, right? So this term goes really high, okay, in comparison to this term. If you plug in all the numbers, right, so you have 1/2, density doesn't change, so that's the same. So really the only difference is that velocity squared. So the one on the right-hand side is much bigger. So what that means is if these 2, so if the left-hand side equals the right-hand side, okay, if they're two equal, and you know that that second component is bigger than this one, then the only thing that must change is the pressures. So that means this pressure P1 must be much higher than this pressure P2. So the pressure in the second narrowed one drops, while the pressure in the first one will increase in order to have these constant. So meaning the left-hand side equals the right-hand side. Okay, so to answer the question, is the pressure in the 1.5 centimeters, so on the left-hand side, okay, is it bigger or smaller? It will be bigger, okay, if you have a much wider radius, okay, and then it will get smaller in the smaller radius. The compensation is that the energy goes to speeding up the fluid, okay, so that means the pressure gets decreased and the fluid actually goes much faster. All right, so that's what you have here. So the answer is bigger, okay, so this is a great question. Now, this also ties in kind of to the last component in here, and this is the last example that I have for you, which is, in this example, if the fluid in the pipe is water, all right, so if it is water, now the density of water okay, is 1,000 kilograms per meter cubed. Okay, we typically assume that unless they give that to us. It changes depending on the temperature, but okay, we'll assume that it's this. The narrowing is open to the atmosphere, all right? So that means that over here, this is open to the atmosphere. So this is at 1 atmospheric pressure. So this pressure, P, is equal to 1 atmosphere. That's what we have, all right? So now, if we know that, then we want to be able to find what the pressure over here is, okay, which is P1. So we're going to have to use this formula, okay, in order to make this work. So we're going to have pressure P1 plus 1/2 the density of the water times the speed that it's moving at on the left-hand side is going to be equal to the pressure P2, which is 1 atmospheric, plus the 1/2 times the density of the water of whatever speed this is moving at. Now we have all of these pieces of information. So on the right-hand side, we know that the pressure is 1 atmosphere. Okay, that's what it's open to. So that is in metric standards. Okay, and we can see it right there. Now the 1/2, this is going to be density is 1,000. The speed that we had, which is 29 point, I hope I kept it. Okay, I did keep it. So 29 point whatever, 29, etc. This is squared. So I have all of this. On the left-hand side, the only thing that's missing is pressure P1. I have 1/2, again, this is 1,000, and the speed, K, is just 3 squared. So I'm just really missing that pressure. All right, so I'm going to have this entire term, all right, this entire term, and this entire term right here. What I'm going to do is I'm going to bring this on the right-hand side to isolate for my pressure. So P1 will be equal to, okay, let's call this term 1, let's call this term 2, let's call this term 3. So it's going to be equal to the term 2 plus term 3, which are on the right-hand side, minus that term 1, which I have to bring over. So let's do that on the calculator entirely. All right, so I'll do that in fast forward fashion. Okay, so there you have it. All right, so it's quite a big amount of pressure. So notice that if it's open to the atmosphere over here, okay, which is 101 kilopascals, notice that over here, okay, it's about 5 times as much, okay, that particular pressure. And that makes sense because of the fact that this is moving so much faster over here. So it has to compensate, and then that pressure, okay, will be there. So now again, if you wanted to round this off to, 2 significant figures, you can certainly do that. So 5, 3, and you can put all of these as zeros, okay, but the hope is that you understand how to set this up. This is a fantastic question in order to understand how Bernoulli's principle comes about, where it balances off pressures and really, okay, the component of the speed. It's almost like the kinetic energy, right, which is stored in there. All right, so thanks for watching. Hopefully we'll see you in future videos. Bye, everybody.